name's Dominic. I'll be talking to you about the first law of thermodynamics for my ENGR 251 project. What is the first law? Essentially, it is what you could say balance of energy. So think of it this way: it is like the conservation of mass principle you've seen in basic physics, but instead here, call it the conservation of energy principle, where if I look at my notes here, energy can neither be created nor destroyed. It can only change forms during a process. So what the first law, I guess, gives us was studies the relationship between various forms of energy and their interactions during a process, right? So, first law of thermodynamics, essentially energy balance of the surroundings going in, and then from the system going out, right? It can be written this way, very simple form. Delta E system is equal to En minus E out, where En is the energy gained by the system, and E out is the energy lost by the system. You can think of it as a balance between the transfer of energy from the surroundings to a system, system to a surroundings. So if a system gains energy, it's lost by the surroundings, gained by the system. If the system loses energy, the energy is gained by the surroundings. The surroundings, I guess, real quickly here, if you have a system, let's say you consider a piston cylinder, that is your system, right? Everything else around it would be the surroundings, I guess, in a nutshell, right? So that's just quickly to hopefully you have a better understanding. The first law can be written, is written this way. So delta E is Q in minus Q out plus W in minus W out plus E mass in minus E mass out. So what these are is Q is heat transfer, W is work, E mass is energy mass flow rate, which I'll explain in a second. First, I want you to pay attention to the sign convention. So when we have E in, energy gained by the system, so that would be a positive value. But if we have energy going out of the system, so leaving the system going through the surroundings, you see here the out values all have a negative in front of them, so that's negative, right? Because the system has lost energy. So, talk quickly to find these values. What is Q, W, and E mass? Well, Q is the heat transfer. What heat transfer is? Well, it's an energy driven by temperature difference. Q in would be the system gains heat, gains a certain gain in temperature, right? So we will increase the energy of the internal energy of the system, thus increasing the total energy of the system. Q out, the opposite, it's heat leaving the system, so leaving to the surroundings, which would make the internal energy of that system smaller than the energy smaller, right? W, well, a quick way to think of it while you're problem solving for work is if it's not driven by a temperature difference, well, it must be work. What work is what you look in essentially in work is boundary work. If there's no work happening with boundaries expanding or compressing themselves, let's say as you could imagine a piston cylinder going up and down, there's no such work happening like that, nothing mechanical that's promoting work, well, then work is not existent in this system. So different types, let's say work in. Well, work in would be characterized as work transfer to a system, work done to a system. So let's say if you look at a compressor doesn't work alone, it needs some sort of mechanical work done to it, or electrical, depending how it's made, to activate this compressor so it could fulfill its duty to compress air, right? And then work out would be work done by the system, so produced by the system. So you could think of a car engine, you can think of hydraulics. Once it gets that work in, then it produces work, right? By moving the piston cylinder, right? Pretty basic examples. So, and mass flow rate, well, mass itself, you might think, why is that an energy? Well, mass flow rate is an energy because mass itself carries an energy. Mass itself is an energy, sorry. It could carry energy if it's in movement, if it's so kinetic energy, if it's at a height, so potential energy, if it's about, let's say if it's about to fall, like a rock falling off a cliff, or if it has some sort of internal energy. Let's say an object has heat going in it. Well, the molecules are agitated, has some sort of internal energy because temperature is high, right? So Hopefully now that's a bit clearer to you. I'd like to talk to you about different processes as well. You have processes called, as I've written here, adiabatic. What adiabatic means is there's no heat transfer going on whatsoever. So no heat transfer in or out. You can, for example, let's say a compressor, because the fluid, which would be the air, is moving so fast that there's no time, there's no resonance time, you could say, inside the compressor where the heat temperature difference is very negligible, or same thing as in nozzles or diffusers, air is going by so fast, temperature difference is very negligible. When you have no work interaction, well, it's, again, there's no boundary work involved, right, which is the basis of work. So let's say a rigid tank with an ideal gas in it, there's no mechanical, nothing, just picture a tank with a gas in it, nothing's moving, nothing's making the gas, or some kind of flow or boundary work, so work would be equal to 0, right? And then, if I look over here, if we have a closed system, the perfect example for a closed system would be a piston cylinder, where that would mean where no mass is going in or out. It's not really a process. This comes more down to problem solving. So your whole your energy, energy of the system would be equal to only Q. Depend only on the heat transfer and the work, as written over here, and not on mass flow rate, because mass flow rate is 0. No mass going in or out. And then you have obviously a bunch of other different type of processes, but to keep this short and simple, yeah, I'm not sure where I was going with that there, but I'll edit that out. Thank you.